So, what is the photoelectric effect? Well, when Max Planck first came up with the equation E quanta is equal to HF, as he says in his own words, it was essentially an act of desperation. That is, he didn't know the reason behind what he was doing. He just knew that what everybody else was doing currently was wrong. And maybe, just maybe, if he did this, something would turn out right. So let's go over that. What did Planck actually do? Where did E equals HF actually help? Now, first of all, I'm going to rewrite F as nu because that's the symbol that was overwhelmingly used for frequency at that time. So once we have that, what did he actually do? Well, first, he started from the equation describing light's behavior in a closed cavity. Notice how similar this looks to the definition of the space-time invariant. That's one small connection from quantum mechanics to relativity. So this multiplied by E had to be equal to 0. So what does this tell us? Well, we can't solve this without one of, as you'll come to see during quantum mechanics, our favorite techniques to solve partial differential equations: separation of variables. We're going to assume E can be written as the product of a function of x, y, z, and time. If we do that, then what do we get? We get x prime prime yzt plus y prime prime xzt plus z prime prime xyt minus 1 over c squared t prime prime xyz is equal to 0. Now we divide everything by xyzt, and we get x prime prime over x plus y prime prime over y plus z prime prime over z minus 1 over c squared t prime prime over t is equal to 0. And what I'm going to do is I can pick any of these. Let's say I pick now y. Let's say I pick y. Then I can just take all the terms that don't contain a y and move them to the other side. And what you'll notice now is that all of the terms on the other side are a function of x, z, and t, not y. While this, on the other hand, is a function of y, not x, z, or t. They share no variables in common, which means that both sides have to be equal to a constant. Now, to see the rationale behind that, let's say we have a of x is equal to b of y. Then we take the partial derivative with respect to x of both sides. We get a prime is equal to 0. We take the partial derivative with respect to y. 0 is equal to b prime. And so the only way for both to work is if both were constants by integration. So there we go. That means that x prime prime over x is equal to, let's call it kx squared. Y prime prime over y is equal to ky squared, and so on. But since t is time, not space, it gets a different variable, namely omega. So, what's itching? Now, once we have that, where do we go? Well, we can solve this differential equation very simply. It's just x prime prime is equal to this constant times x, which means that x is just this exponential function, e to the kxx. And the thing for, this should be lowercase, y and z. Time is slightly different, but not greatly. we have that minus 1 over c squared t prime prime is equal to omega squared t, which means that, oh wait, the c squared is included. So t prime prime is equal to omega squared t, which implies that t is just e to the omega t. It's not that groundbreaking. So everything's fine so far. Now we introduce boundary conditions. Namely, since light is always going to be inside the box, it's never going to escape the box. It's never going to reach the boundaries, which means that x of 0 has to be, well, 0. Y of 0 has to be 0. Z, 0. And of course, the box is finite. It's a finite volume, which means that there's going to be a limit in the x direction, a limit in the y direction. Let's just call it Lx, Ly, and a limit in the z direction. And of course, when you come to grips with that, that means this won't do. No exponential function is going to be able to have two zeros. But there is another solution, of course, a linear combination of sinusoidal functions. It could always be sine of kxx plus cosine kxx. There's definitely an amplitude here, but I don't have space to write it, so that'll be for another time. Sine of kyy plus cosine of kyy. And we have sine kzz cosine.
Isaac, you're blocking everything you write.
Kzz. These boundary conditions don't necessarily apply to time, so we'll leave time be for now. So with that, what do we get? Well, since this has to be 0 at 0, that means the cosine part can't exist, because cosine of 0 is 1. So this has to be crossed off, that has to be crossed off, this has to be crossed off. X is just this, Y is just this, Z is just this. And same thing, well, not the same thing, but we can use these boundary conditions to deduce more about what kx, ky, and kz are. Namely, we know that sine kxlx has to be equal to 0. When is sine equal to 0? Well, of course, when whatever's inside is an integer multiple of pi. So that means kx is limited. Now, it might be worth noting just exactly what we're trying to do here. We're trying to find the number of radiance modes or radiation modes given a certain frequency inside a fixed volume. And how are we doing that? And what are radiance modes? Well, think of normal modes. If you have light bouncing, why does it make that noise? If you have light bouncing around in a box, there are some patterns it makes which are completely random, but a few patterns it makes that are totally periodic. And if it makes those periodic patterns very often, that's a very gross oversimplification, but it works. Those periodic paths are called normal modes, where essentially the entire system is oscillating with one frequency. So we want to find the number of these normal modes. This is actually just an estimate. This is the derivation of the Rayleigh-Jean law, actually. We can't really know the true number of normal modes, but this is an approximation. And as you'll see, while of course normal modes are normal modes, you can count how many there are, it's an integer number, we're not going to get an integer out of this. But that's fine because this is an approximation. It's basically just multiplying the frequency of radiance modes by the volume. And of course, sometimes, just like multiplying the population density of a city by its volume, that's not going to give you exactly what you want. That's my system. So now that we know that, we can continue moving onward. But what onward things are we going to do? Well, the last thing to do is realize that, light can't go anywhere when t is equal to 0 as well. Light just can't exist. So when t is equal to 0, this has to be equal to 0. And of course, we can't add a constant here. So what do? Well, we replace this again with another thing that looks like sine omega t. Now, this time we don't have as many boundaries on this. But note that by definition, omega is just going to be 2 pi nu, where nu is the frequency. Now, here's where things are going to start getting a little bit rough. So we calculate the number of modes this way. We're essentially just taking n. And what is n proportional to? Well, it's going to be dependent on what's in here. We get that n is just going to give us, oh wait, why am I using n? Sorry. So we're going to get n is equal to Lx kx over pi. It's going to be equal to Ly ky over pi. It's going to be equal to, oh, and actually these two are not equal. That isn't necessarily true. We have different n's. There's an nx, there's an ny, and there's an nz. And when we have those three, we can essentially combine them to get a single n. N is equal to the square root of nx squared plus ny squared plus nz squared. So, at the end, what you have to do is take the pi out and let the blood in. What we end up finding is that if we have n is just the amount of space in the cell and dn is the thickness, this is proportional to the frequency. So what we end up getting is n dn is the frequency squared multiplied by the frequency, or d nu, multiplied by some constant. But what is that constant? Well, it's pretty simple, actually. It's just going to, n squared then is just going to give us nu squared d nu multiplied by some constants. And what are the constants going to be? Well, consider that if n is equal to some constant multiplied by nu, dn is just equal to the same constant, dn. So, this is just going to be that constant cubed. And what is that constant actually? Well, we're going to find 8, 2 cubed, pi over L cubed, C cubed. That, oh, wrong. That right there is the number of radiant modes. Well, it's an approximation. And this approximation is all nice and good, but here's the thing. If you have the perfect black body like the one described in the problem, and you start emitting lower and lower frequencies, what is nu squared, higher and higher frequencies, lower and lower wavelengths, what is nu squared going to look like? It's going to keep going up. It's going to diverge. But what the experimental results were showing is that while our results were correct in the beginning, it doesn't diverge. It peaks and then it plateaus. Well, it goes down and then it plateaus. So clearly, something's going wrong here. So what is? Well, everything starts going a little bit more right once you introduce the notion that energy is not just this continuous function. It has to come in packets, quanta. That's where the name quantum mechanics comes from. Those quanta are h nu, where force E equals h nu comes from, which means that the total energy is just going to be n for some integer n. I should probably use a different n. H nu. And once you assume the energy looks this way, you take the partition function. Now, originally, energy, E, was calculated as a ratio of two integrals. What you'll notice is that if you assume that there's this rigid structure, everything has to be multiples of h nu, then integrals are not the play. You instead have to work with sums over n. And of course, once you work with a sum, instead of the exponential functions canceling out and you getting the original results, what you're going to get is an actual exponential offset. And when that exponential offset is accounted for by, multiplying it in with the whole separation of variables stick, when you now say E is equal to x, y, z, t multiplied by this, and your solution now looks like c v nu squared e to the minus n h nu minus 1, nu cubed. What you get is that, well, everything's exactly the same for small values. So Planck's equation looks like this. But the exponential term will outgrow or outshrink the cubic term as nu grows large. And cancel it out, the denominator grows, and eventually it goes to 0. And I think you can see that Max Planck's assumption really fitted the data a lot better than the Rayleigh-Jean law. But now we come to the question of why? Planck himself, as I said in the intro, said this was an act of desperation. He didn't know what he was doing when writing this down. And it ended up being a very controversial act. A lot of it saw it as pretty much ad hoc. It's not real physics because it was a guess. Until in 1905, just 5 years later actually, Einstein put a reason into the madness. So what was that reason? Well, let's introduce the photoelectric effect. What Einstein found was that electrons in these materials were consistently being brought down by a certain number of energy levels when they were exposed to light. They weren't sometimes brought down one energy level and then sometimes one half. They weren't brought down two energy levels and then going up by 1/4. They were constantly, consistently losing energy at these fixed intervals. And of course, what that implied was not just that the electrons were working on quantized amounts of energy, but that the light that was knocking them out, knocking them between the different energy levels, had to have exactly that amount of energy stored inside them. And so the light's energy had to be quantized too. Einstein stated himself, the wave theory of light will probably never die in the paper about the photoelectric effect, but my experiments have found that a continuous model of light's energy is not consistent with experimental models. That is, the discrete model works better. N8 nu was the answer to this dilemma. And of course, as I introduced last time, people then started asking, well, if waves can behave like particles, why can't particles behave like waves? And that was only further confirmed by doing the double slit experiment with electrons, where electrons are obviously particles. They can't act like waves, and yet they did. Then the experiment was done with light. And I mean, light at that point was thought to be a wave. It can't act like a particle. So, as you can see here, the lines between waves and particles were blurred. In fact, that line was completely broken and disproved by de Broglie, who stated that every particle has this wave function that describes it. Every particle essentially is a wave. Every wave is a particle. So quantum mechanics is defined by that blurring of lines between what is and isn't solid matter. Everything that we describe in quantum mechanics is a fuzzy wave function. You never know where something precisely is. All you can do is study the probability distribution. So this is all about the history and backstory of quantum mechanics. Now it's time to jump into the first video of quantum mechanics. Thanks everyone for watching, and we'll see you in the next one.